going through the book 50 Challenging Problems in Probability. And this is question number 14, collecting coupons. So coupons in cereal boxes are numbered 1 to 5, and a set of one of each is required for a prize. With one coupon per box, how many boxes on average are required to make a complete set? I think the easiest way to think about this is think about it by breaking it up into stages. So let's say we're at stage 0 where we haven't opened the box. So there are 5 possible coupons, 1, 2, 3, 4, or 5. When we open this box, what is the probability that we get one we haven't gotten before? Well, the probability we get one we haven't gotten before is 5 over 5, right? We haven't opened any, so any coupon we get will be new. Now in our next stage, we've already gotten one. What is the probability that on our next box open, we get a coupon we haven't gotten before? And the logic is kind of the same. We've already gotten one, so there are 4 other possible choices that would be new to us. So it's 4 out of 5. It's a 4/5 probability we get a coupon we haven't gotten before. And this logic continues iteratively. You see at each stage, there's a probability that we move on to the next stage, right? And we can kind of look at this almost kind of like in a Markov chain way, where if we write the probabilities of returning back to that stage, the total probability that is essentially going out would be 1, right? So essentially, like let's pick stage 2. If we want to go from 2 coupons to 3, there's a 3/5 probability when we open that box that we actually get a 3rd fresh new coupon. Now from this visualization, there are a couple ways that you can find the total expected number of boxes we need to open. At first, I set up recursive equations, and although they are heavy computationally, you do get the same answer. But in this video, I wanted to find random variables, and specifically I wanted to find geometric random variables. All right, so let's have x sub I be the number of independent trials until first success after getting I coupons, right? And let's just say a success is getting a fresh new coupon, right? One that we haven't gotten before. So for example, x sub 0 is essentially the number of independent trials until our first success after getting I coupons. And that probability will be 5 over 5 like we calculated above. If we can define all 5 of our geometric random variables, right? So we define all our random variables, and then I also define this new random variable, t, which is gonna be the total number of boxes. And each of these geometric random variables has an expected number of trials, each xi's expected value, right? So we want the expected value of t, which is our expected total number of boxes. And due to the linearity of expectation, we can kind of imagine we distribute this expectation amongst each of our 5 random variables. And we know the expected value of a geometric random variable, right? It's just 1 over the geometric random variable's probability. This should kind of be intuitive, right? Let's say we're at stage 4, where we've already seen 4 of the 5 coupons. So we have a 1/5 probability of getting to stage 5. On average, that should take us 5 times, right? Say we're flipping a coin, we have 1/2 probability. On average, to get a success that we want, it's gonna take us 2 times. When we compute the 1 over p's, essentially it's just the reciprocal of each of the probabilities. And when we sum them together, we get 137 over 12, which is approximately 11.42. So our expected total number of boxes is about 11.42. Thank you.